Welcome. We are going to talk today about nuclear reactors. So we've just talked about how atomic bombs are built, but we want to talk about how can we use that same process of a nuclear reaction and get energy out of it that we can use to power all of our electrical outlets. So I want to talk about nuclear reactors, and sometimes when we think about nuclear reactors, I think of The Simpsons and Homer holding on to some kind of nuclear fuel. So we'll talk a little bit more about exactly how it all works, and we don't have a lot of Homer Simpsons running the nuclear power plants, thankfully. First, I want to remind you how the nuclear fission, or breaking apart of an atom, works. So we start with, in a nuclear bomb and in a nuclear reactor, uranium that weighs 235. So it's got 235 protons and neutrons inside of it, inside of its nucleus. Now when a slow-moving neutron comes by and touches it, that slow-moving neutron can stick to that nucleus to make it have 236 particles. And when it has 236 particles, uranium-236, it tends to break apart. And when it breaks apart, these smaller daughter atoms, in this case krypton and barium, move very quickly. They have a lot of energy, and 3 more neutrons are given off when it splits that also move very quickly, or we call those fast neutrons. Because those things move very quickly, like these daughter nuclei, they bump into other things, they have a lot of energy, and it gives off a lot of heat. Now, the one thing I want to make sure that we're clear of is that this neutron needs to be slow moving. If it moves very slow, then it can stick to uranium to make uranium-236, and it can fall apart. If it moves too fast, many times it just skips right off or moves right by it and does not stick to the uranium-235. So if that neutron's moving too fast, this reaction won't work. Now we said that this gives off 3 neutrons. If one of those neutrons hits another uranium, the reaction can occur again. If 3 hit, then the reaction can get out of control and maybe blow up like an atomic bomb. That's what we try to do when we have an atomic bomb. How often one of these other uraniums gets hit is determined by how much uranium-235 I have. If I have a bunch of uranium-235, it's more likely that this would happen. If I have less uranium-235, it's more likely that only one will hit it and the reaction keeps going. So first, let's review how much uranium is out there naturally. So in all uranium, how much of it is uranium-235? And we said last time that uranium-235 is only 0.7% of all the uranium you get. Most uranium is uranium-238. This is uranium that is not used, that is not fissile, that cannot break apart, it cannot fission. So we need uranium-235. So this is the kind that's used in a bomb or a power plant. For a bomb, we need a whole bunch of uranium-235 together, so we tend to enrich it a lot. We make it, the uranium we use for a bomb, like on a nuclear submarine, might be 90% uranium-235, where we've used centrifuges and we've purified it, so most of it is uranium-235. That way, when the 3 neutrons come out from the first fission, they're more likely to hit another uranium-235, and the reaction can blow up whenever I want it to. A power plant does not use that much that enriched uranium. It tends to use regular uranium, like only 0.7%, up to 3 or 4% uranium-235. So let's talk about how a nuclear power plant works then. Okay, the first thing we said is we need the neutron that hits my uranium-235 to be slow moving. If it's slow moving and it sticks, it can fission, break into 2 smaller parts, and 3 more neutrons can be given off that are moving very fast. Now, those fast-moving neutrons, they move so fast, they would just leave my reaction, never stick to another uranium-235, and my reaction was shut down. So the first thing I want you to realize is that if the reaction gets out of control and these neutrons move too fast, they don't hit or stick to another uranium-235, and the reaction cannot keep going. I cannot split any more uraniums. This only works if I slow down these fast-moving neutrons. So there are ways for us to slow them down. Inside of a nuclear power plant, we don't just put uranium-235, we also put some other material in there called a moderator that would help slow down the reaction. So in this case, here's the dark blue purplish color. I'm not good with my colors. It has uranium in it. And when uranium fission happens, I get two smaller particles that move very fast and give heat. That's the energy I need, heat energy. And it also gives neutrons that move too fast. And those neutrons would just leave the fuel and escape, and my reaction would shut down. So we tend to put some kind of moderator that it's some other material that has a bunch of atoms in it, that the neutrons could come into that and bounce off of the atoms in there, lose some of their energy to slow down. So I need to slow them down. So moderators could be all kinds of different materials. They've used many different materials. What we tend to use now, most often, is water. Different types of water. In the United States, we tend to use just regular water. So we can use water, and that will slow down the neutrons enough that, so in this case, the neutron comes, it bumps into the water, slows down, bumps into more water, slows down, and enters another uranium fuel rod. That neutron will hit another uranium-235, and if by this time it's moving slow enough, it can stick to it, it can fission and give off more neutrons and energy, and then they go into more water, slow down before they hit another one. And we just keep moving that water. The water heats up, so we keep moving that water out and putting cold water back in. Water is okay slowing down neutrons, but it's not great. Water just has an oxygen atom and these tiny little hydrogens, so oftentimes the neutrons will just slide by, and so we can slow them down enough to make this capture happen, but it's not the best way to slow it down. But it's cheap, and it's a good way for us to do it. In this picture, the other thing you want to make sure too is only one neutron hits another atom. One neutron hits another atom, so it is self-containing or self-sustaining, self-propagating, but we don't want it 3 neutrons to hit. We don't want it to get out of control. So another thing we do is we have what's called a control rod. And a control rod is something that I can put into the reaction or take out of the reaction. And a control rod is a material that can absorb neutrons, but itself isn't like uranium that could split and become and it can fission. So we tend to use like boron or cadmium, different types of control rods. So if the reaction's going too fast, I can lower these control rods in, absorb the neutrons. If I want it to speed up a little bit, I can let the control rods out and let the more neutrons stay in there and control the reaction. But we always have the control rods ready that if the reaction seems like it's getting out of control, we just drop them all in and immediately shut down the reaction. A lot of times we have a bunch of control rods in the reaction ready to go down. And at times you have to replace some control rods because they've absorbed so many neutrons. You have to put fresh control rods in. Now, in these reactions, nuclear reactors, we always keep at least 30 control rods in there. Never, ever do we take and go less than 30 control rods. But there are many control rods. If the reaction tends to get too hot, and sometimes that's happened in the past, and the fuel starts to melt, so let's say we take all the control rods out, and the reaction gets too hot, it could melt together, the fuel rods, and we call that a meltdown. It can get too hot, it can go through, go back here. And it can melt and go through the reactor and can cause an explosion of some sort. So we want to prevent that from happening. Okay, let's make sure we've got this down. My uranium has uranium-235 in it. It might have 0.7% up to 3 or 4% uranium-235. My moderator tends to slow the neutrons down because if these neutrons are moving too fast, they never stick to more uranium-235 and the reaction shuts down. So the nuclear reaction can't keep going and can't explode like a nuclear bomb. They have to be slow-moving neutrons for this to work. The moderator tends to slow down. We use either water or we can use some other types of moderators that slow neutrons down even better. The control rods totally absorb neutrons. They don't just slow them down, they absorb the neutrons. So that we can shut down a reaction using control rods. We can speed it up or we can slow it down using control rods. All right, so this is how a nuclear reactor works. So let's go back into history. It's World War II time, and we have the idea that if we can slow neutrons down, we can maybe make a self-sustaining reaction. Some great minds, some scientists got together and said, let's try this out. For the moderator, they decided we're going to use graphite. Pure carbon graphite is a good moderator. They also use graphite as control rods to slow down a reaction. So the first time this happened, it was in Chicago, it's at the University of Chicago, under the bleachers of the squash court. So imagine you're at AU, and we go underneath the bleachers at the football field, and we try the first nuclear reaction that would be self-propagating. Now, this picture here in the bottom left is Enrico Fermi. Fermi was the main scientist in charge of this. So they called this nuclear reactor the Chicago pile. A pile is a nuclear reaction. And in the Chicago pile, they took a bunch of graphite with holes in it, where they put graphite-containing uranium rods for the fuel. So all of the whole pile, all this graphite, there's a bunch of moderators that would slow the neutrons down. And they did the calculations to figure out how slow they need to make it work. You can see here in the bottom left of the Chicago pile, there's a hammer laying here, so you can get a feel for how big it is. And here's a famous painting of the Chicago pile when it actually went. Now, a few things I want to show you. A couple of interesting parts. There was a graduate student up on top of the Chicago pile, and he held there was a keg cut off at top, and it had a bunch of boron solution inside of it. And he stood on the Chicago pile when they got it going to see if they can get the first nuclear reaction to occur. He was the original dead man switch. The reason he was up there was if it got out of control and he happened to die, he would fall over, spill the boron solution, and boron's a control rod, a type of control, and it would immediately shut down the reaction. They were pretty sure they knew what they were doing, but they could have been off one way or the other, where they thought it could have gotten out of control, maybe who knows what would happen, or it wouldn't work at all. But it actually started to work, and the Chicago pile gave off energy. They were able to measure it, and they could get a self-contained reaction. The other thing about this painting that is famous is that out of all the scientists looking at the pile, Enrico Fermi is looking the other way. Legend has it that Fermi was sitting there doing calculations with the slide rule, which you would do at the time, and he said, yep, this is going to work, let's go to lunch, and he left. But the Chicago pile did work, and that was the first self-sustaining nuclear reaction, atomic reaction. So they showed it would work. Okay, now let's go back to our nuclear reaction. We know that we need moderators to slow down the neutrons, because if the neutrons go too fast, the thing explodes. No, that's not true. What did I say that was wrong? If it slows down the neutrons, because if the neutrons get going too fast, it does not explode. See, that's a common misconception. What happens is the neutrons, if they go too fast, just cannot absorb, and the nuclear reaction shuts down. So that means that my nuclear reaction cannot explode like a nuclear bomb. Remember, we said that 90% of uranium you needed in order to make an atomic bomb, uranium-235. Our nuclear reactors have a much less amount of uranium. We don't put that much uranium-235 together. So our nuclear reactions cannot, in a nuclear power plant, cannot explode like a nuclear bomb. It's impossible. We don't put that much uranium together. It's not a supercritical mass of uranium-235. And if the neutrons get going too fast, the nuclear reaction shuts down. Now, we do have to get the heat away from this, because if it gets too hot, we can fuse the fuel rods and they can melt. And there was a pretty bad movie back in the late 70s called The China Syndrome, starring Jane Fonda, I believe. I'm not sure. But anyways, the idea was a nuclear power plant, and there was a meltdown, which means that nuclear reaction gets out of control, the fuel heats up, And this can happen. If the fuel gets too hot and it melts, then it can go right through the bottom of the reactor, and the idea would be it could melt right through the ground all the way to China, the China syndrome. It can get so hot, it is possible, if the safety features are taken away, that it can get so hot it can heat up, can melt through the reactor, and could cause a chemical explosion. This is what happened in Chernobyl. We'll talk about that in a bit. But it cannot, I repeat, cannot blow up like an atomic bomb. It's impossible. There's not enough uranium-235, and if the neutrons get going too fast, they just escape. And it's hot, but they escape, and it cannot keep going like a nuclear bomb. All right, now let's talk about the two main types of reactors. In the U.S. and most other places, we use what are called water moderators, just regular H2O water. Now we find that with regular water, we slow the neutrons down quite a bit, but there's still so many of them escaping that we have to have a little bit extra uranium-235 around in order for those neutrons to hit another uranium-235. So in the U.S., we take our 0.7% uranium-235 uranium, and we use our centrifuges, and we enrich it a little bit to get to 3%, 4% enriched uranium-235. It's got a little bit of extra uranium in there. Now, we make nuclear bombs in this country. We have the technology to enrich the uranium. We have the centrifuges. So it's easier for us just to enrich the uranium than to use special water. Now, there are other places that say we don't want to use centrifuges. We don't want to enrich our uranium. So like in Canada, they use a different type of reactor called a CANDU reactor. So instead of using regular water, they use water, but instead of regular hydrogen that weighs 1, they use hydrogen that weighs 2. It has 2 particles in every hydrogen. So instead of H2O, it's called D2O, or deuterium water. Sometimes we call this, since the deuteriums are hydrogens that weigh twice as much, we call this heavy water. It weighs a little bit more than regular water. Now, heavy water is not radioactive. We can get it from the oceans, but we have to do some chemistry to make heavy water. But if you use a heavy water as your moderator, with the deuteriums, it takes a little bit more away of the energy away from a fast-moving neutron and slows it down a little more. Because heavy water works so well at slowing down neutrons, they can use unenriched, not enriched in any way, uranium. So they put regular uranium from the ground, 0.7% uranium-235, and that's enough uranium-235 that if you use heavy water, you can slow down the neutrons enough that it will be captured by another uranium-235. They call these Canada deuterium heavy water reactors CANDU reactors. Canada and deuterium, so you get CANDU from those. This brings up an interesting point. Iran, we're told that in Iran, it's not fair that they can't have nuclear reactors, that everybody should be able to have a nuclear reactor. So the idea is they should be allowed to, their argument is they should be allowed to use centrifuges in order to enrich uranium so they can have a power plant. But we saw here that you do not need to enrich uranium ever in order to have a power plant. All you have to do is use a different moderator, heavy water, which is available everywhere and easily available. The idea is if you have centrifuges, you can enrich a little bit to use a reactor kind of like we do use in the US. But there's nothing to keep somebody from keep using that reactor to keep enriching and purifying the uranium to get to 90% uranium-235 to make atomic bombs. So it's interesting to me. I'm not sure of the politics, but the idea that we allow some rogue nation to have centrifuges to be able to enrich the uranium seems to me to be a dangerous proposition, because you don't need to enrich the uranium at all in order to have a nuclear reactor. So I'm not sure what's going on with the politics, but I do know you can use regular uranium and never use a centrifuge, and you can still make a nuclear reactor. Okay, let's talk about how the nuclear reactors work then. We got the idea of what's happening inside of the plant itself. Here's a nuclear reactor. There's a building, a containment building, where the nuclear reaction occurs. And we use a special building that if it's going to blow up, hopefully it would contain the reaction and not blow up like a It can't blow up like a nuclear bomb, but it could blow up like a regular chemical TNT bomb. So hopefully we can contain it in there. The thing what we do is we heat up water. We use the steam that comes off of that heating up, and we rotate a turbine, which can make a generator, which can make our electricity. We'll talk about that more in the next chapter. All the radioactivity stays in the containment building. We can just keep putting new, fresh water in there. The water slows down neutrons, but the water does not get... so anyways, the water slows down the neutrons. The water that we heat up to make the turbine go, so we heat up this water. We just heat up regular water that we get from some water source. We make steam that turns the turbines to make the reaction go. Whenever you see a picture like this part on the left is usually the scary part that they try to show you to make you see that look how much pollution nuclear waste is giving and how terrible this nuclear reaction is. What I want you to realize is this little dome over here, that's where the dangerous part is. That's the nuclear containment facility. This is where the nuclear reaction occurs. Inside here, we're spinning big turbines. We're heating up water and boiling water. But this part over here is just boiling water. And what you see coming out of these stacks is just water, steam. It's perfectly harmless. There's no radioactivity in here. There's no smoke, carbon dioxide. It's just water vapor. So this is like the cleanest part of the entire process. In fact, compared to like a coal burning plant, here we just have steam coming off. There's no carbon dioxide, which could lead to no types of global warming greenhouse gases. It's just steam. The only dangers really are so it's perfectly clean coming off. The only danger in a nuclear power plant is if there's a breach in the containment facility. So let's talk about ways there can be a breach in a containment facility. One is if we allow the nuclear reaction to get too hot. It cannot blow this thing up like a nuclear bomb, but it could melt the fuel rods. You could have what's called a meltdown, like in the China syndrome. It can melt through maybe the cement block floors and cause some kind of explosion. Most of our containment facilities are built to try to withstand that sort of thing. That's one way you can have a problem. So let's look at, there are mainly three main bad times when this went wrong. So let's kind of look at each of those scenarios because we want to weigh whether we should build these or not. The first and the biggest of all time, the King Daddy bad decisions going wrong, where a nuclear reaction got out of control and caused a lot of damage, is Chernobyl. Back in 1986, in Chernobyl, they had the worst nuclear accident of all time. And here's what happened. In Chernobyl, there was a nuclear power plant. And the Russians had gotten pretty cocky. They thought they could totally control this. Their containment building was just a cement block building. It wasn't built the way most containment buildings are built nowadays. And they decided to run a test. So on April 26, 1986, they decided they just had a question. They wondered, how long will the generator turbines keep running if we lost power? So they did a safety test. How long will these turbines keep going if we lose power? So the first thing they did three things, and they had to do all things stupid in order to make this happen. First, they decided to turn down the power. And so they dropped their power, but they dropped their power too far. The second thing they did was they took their control rods, and remember I said there are a bunch of control rods in there. In order to make the reaction go faster, they wanted to see not only if we lost power, but what if things started to overheat. They lifted the control rods out. And I said you always, always, always keep 30 or more control rods in, but they took them all out except for 6. Only 6 control rods remained. And then the other thing, the cooling water that goes and keeps this thing cool, they said let's turn that off as well. So they turned off the cooling water, they took out all the control rods, and they dropped the power to see what would happen. Now what happened is what you would think would happen. The reaction started to heat up. the nuclear reaction started to heat up. Now the neutrons started to escape. It didn't blow up like a nuclear bomb, but it started to get too hot, and what they had was the fuel just melted. Before they could get the water turned back on and the control rods dropped in to stop the reaction, the fuel rods melted. It melted through the containment building and caused an explosion. And you can see here, this is the containment building in a regular looking cement block building. And it blew out like a regular chemical explosion would. Notice there's still a lot of buildings standing. If this is a nuclear bomb, this would be totally flat. That's not what happened. It blew up like a regular chemical explosion, but it blew all of that fuel, that radioactive fuel, into the environment. And it blew all over the place. And so Chernobyl was a terrible accident. I think there was something like 10 tons of burning radioactive fuel was blown about 3,000 feet up into the sky. The winds picked it up and started carrying it. We thought there may be all kinds of cancers from this. In fact, though, is the worst accident of all time. We rebounded pretty quickly. There were much fewer measurable cancers than we thought, but it was a terrible mistake, and it was based on getting too cocky, not having the right safety features, and breaking all the safety rules led to the Chernobyl accident. So Chernobyl was very bad. Let's see. Anything else about Chernobyl? No. Let's move on to the worst accident ever in the United States. So we were building many nuclear reactors back in the 1970s because we realized they give off no, we're not burning fossil fuels, so that gives off no carbon dioxide. There's no smoke, no air pollution that occurs from them. But something could go wrong, like happened in Chernobyl. Our worst accident happened at a place called 3 Mile Island back in 1979. So this is in near Harrisburg, Pennsylvania. This is a picture of 3 Mile Island. And again, what happened was we had a coolant loss. So the water that helps keep things cool started to escape, and we had coolant loss. The fuel rods started to fuse slightly. So we had warnings that this was going on. We didn't realize it at first, so we had slight cooling or slight fusing of the fuel. So we dropped it. We said drop the control rods in immediately. They dropped in. We weren't sure they went in all the way, and if the reaction was totally shut down. It's a really interesting thing to watch. The president at that time was Jimmy Carter, who used to work on nuclear submarines. Jimmy Carter actually flew in and to try to calm everybody down. We've got this under control. I bet the Secret Service is like, Mr. President, we got to get out of here. We're not sure this thing may blow up like Chernobyl will in 7 years. But so there was a slight fusing. The other thing you've got going on is when the water, you get the steam start to build up, the steam inside of the coolant steam and the steam used as the water used as a moderator inside the nuclear reactor itself, not the steam that escapes, that's a different water source, but the steam inside is a little bit radioactive. Now the containment building was set up to be able to handle so much of that pressure. What they ended up deciding to do is what they didn't want was for the hydrogen that was made to blow up and blow it up like it would at Chernobyl. So they made the decision that we're going to release a little bit of this radioactive hydrogen and steam into the atmosphere so our containment building does not blow up. So they released some of it. Now, anytime you make that decision to release radioactivity into the atmosphere, it's very bad politically. It's a terrible thing to have to do politically. It was probably the right decision because if the containment building blew up, all that radioactive material would have spilled out and blown into the atmosphere, and you would have had a Chernobyl issue on your hands. The background radiation from that ended up adding 8 millirems of radiation to the surrounding area out to 10 miles out. As a comparison, if you live in Denver, Colorado, your background radiation over the course of a year is 3,600 millirem. So we added 8 millirem to the folks in the area. Probably, well, you can do the calculations. I tell you how to do that. Nobody died from that unless they died from being too worried about it. but nobody died from that amount of radiation. But I taught you previously how to do the calculations. Ever since 3 Mile Island happened, we've not built any more nuclear power plants in the United States. So instead, we decided to burn fossil fuels instead exclusively. We're starting to get into the solar and wind, but the decision politically really needs to be made. Do we allow nuclear power plants that do not add to any global warming, they do not add fossil fuels burning? Eventually we might run out of fossil fuels, but we don't use much uranium. So anyways, it's a political thing. My personal bias is I think we should build more power plants. That's me speaking. I think it's clean energy. I think it's safe. But that's what happened at 3 Mile Island. The worst was Chernobyl. 3 Mile Island, a little bit of radioactive gases escaped, a slight fusion of the fuel rods, but it did not explode. 3 Mile Island did not explode. The other big accident that's happened more recently was in 2011, Fukushima. And this is a power plant in Japan, and they had built it where they were ready for any kind of earthquake up to a magnitude 6 earthquake, I think. They had an earthquake near Japan that was greater than any earthquake they could have imagined. So they had an earthquake of thousands of times more energy than they imagined. They are ready for when an earthquake like that happens. A tsunami could occur. So they had walls up, ready for a big tsunami. But what happened was they had a much bigger earthquake. The tsunami was much greater than they imagined, and the waters came over the walls. So they lost power at Fukushima. They were ready for that. They had backup generators, and they had backup generators for their backup generators. So they were ready to keep the coolant water going, all the pumps going, to keep their nuclear power plants going. The problem was the flood waters that came in from the tsunami were so great that the water was so high that they flooded all of their backup generators. So they lost all their backup generators. So they lost coolant water in the nuclear power plants, and the fuel rods started to heat up. Again, it cannot blow up like a nuclear bomb, but the fuel rods started to heat up, and they had no backup generators, and they couldn't get backup generators there because all the roads were flooded. So what they did was they brought in a bunch of boats and started shooting water at it to try to keep it cooled down until they could get the power back up. In hindsight, anyways, it starts to heat up. They had to make the same decision we made at 3 Mile Island, and they decided to vent some of the radioactive gases. But in the end, so they tried to cool it down from the water, but it ended up getting so hot that 3 of them did blow up. They had some explosions. 3 of the plants, they had several plants here, released some radioactive fuel. The containment contained most of it, and not near as much radioactive when it exploded. Mostly hydrogen gas that was radioactive escaped, not the actual daughter particles, the fuel itself. It was contained. Hydrogen gas escaped, so there was a more of a radioactive release than at 3 Mile Island. The problem is, in Japan, there's many populated areas, so again, this is a bad accident. What we learned from this is maybe you don't want to put nuclear power plants near too many people. You may not want to put them where the Ring of Fire is in Japan, although Japan still has them. And you need to have your backup generators very, very safe. So you need to have them set up where they cannot be flooded in some way, or much higher. You got to be able to keep your power going in order to control this. So Fukushima, a pretty bad accident. Anyways, that's how nuclear power plants work. The things you've heard me say many times, I want you to know, a nuclear power plant does not have enough uranium-235. It cannot explode like a nuclear bomb. You can, if you're not careful, have a meltdown. We build containment buildings much safer than we did during the Chernobyl days. We have many safety features in place where we wouldn't do something stupid like we did in Chernobyl once again. Although anytime you build something more idiot-proof, we always prove that we get better idiots. So that's the issue. Nuclear power plants do not give off greenhouse gases. Only steam, which is not radioactive, is given off. The only dangers is if you have a meltdown and you have a breach in your containment system, your containment building. Can't blow up like a nuclear power plant. We also see with what happened in Fukushima that you got to keep the backup generators. And if you have something that is 10,000 times worse than you can dream, that you could lose your backup generators. I think in the end, Fukushima is mostly a success story that it was 10,000 times worse than anything they could imagine, yet they still had very little radioactive leak. So we're getting much better at building our containment buildings. Okay, it would be great if instead of these, well, let me just stop there. This is how a fission plant works, and I'm going to make another little video that will talk about how we can make even better nuclear power plants that would not use fission. So we're going to stop there.